Okay, before we can get into the actual solving, I want to just review real quick on what we're going to do with square roots of things that are not perfect squares. So in order to solve these nice simple x squared equations, how do we undo a squared? We square root both sides. So when left with something like 48, it's not 49, which would be a nice perfect square. We've got to break down the 48 into what times what equals, looking for factors that we can pull out if there's in pairs. So we're looking for factor pairs. So for example, 48 could be broken down into 8 times 6. But 8 can be broken down into 2 times 2 times 2, and then 6 can be broken up into 2 times 3. So 6 times 8 can be broken down into this prime factorization. Then we're hunting for perfect squares, for pairs, because 2 times 2, or 4, the square root of 4 is just 2. If we have a pair, we can pull that number out. If we have another pair, we can pull that number out. And whatever doesn't have a pair is going to stay underneath. This final simplified radical is 4 root 3. Now, what's a quick and efficient way of doing this? If you can see that 16 times 3 equals 48, if you can see that perfect square that's embedded in the 48 as a factor, the square root of 16 is just 4, root 3 stays underneath. Your job, if you want to do it the most efficiently, would be to hunt for these perfect squares within. So same thing here, square root both sides. And then break down the 24. The efficient way would be if you could see the root 4 and the root 6. And since 6 cannot be broken down into anything further, it's done. But again, if you don't see this more efficient way, then you break it down into its smallest parts, 2 times 2 times 2 times 3. You look for the factor pairs, and the rest stays underneath. Whichever way makes more sense to you. Here, let's break it down. How do we break down root 500? So again, you might see it as root 100, the perfect square, times root 5. Final answer is 10 root 5. But if you don't see that, break it down into its smallest parts. 5 times 100 would be 5 times 10 times 10, or 5 times 2, 5 times 2. Look for a pair. Look for another pair. Keep the 5 underneath. Final answer is 10 root 5. Either way, which way makes more sense to you? Over here, this one is a perfect square, but it's got a negative. Remember that the definition, square root of -1, is equal to imaginary number, I. And so when we break this guy down into its parts, root -1 times root 36, we're going to get I, but then the square root of 36 is 6. So final answer for this one is 6I. This one over here can be broken down into the root -1. And then for 12, it's 4 times 3. So square root of 4 is 2. Square root of -1 is I. Root 3 stays underneath. Now, root 29 cannot be broken up into anything. It's a prime number. So for this one, root -1 and root 29, all you can pull out is the I. Now, all of these answers are plus or minus that number. So don't forget the plus or minus on all of these answers. So this one right here is x is equal to plus or minus 6I, plus or minus 2I root 3, plus or minus I root 29. So don't forget plus or minus on your answer. Okay. Now, what is the discriminant and what does it tell you about the roots of a quadratic? So the discriminant is part of the quadratic equation. B squared minus 4AC, it is part of the full quadratic formula. And it is what's under the radical. What does it tell me? It tells us how many roots we will have. So for example, if you get a positive discriminant, that means you will have 2 real roots. If you have a 0 discriminant, you will have 1 real root. And if you have a negative discriminant, you have no real roots. When you have a negative under a square root, you have imaginary square roots. So the discriminant can tell us how many roots we're going to have and what kind. So let's go look at some actual examples using the discriminant. So you need to get A, B, and C for each equation, and then plug into the equation. So b squared, don't forget the negatives, minus 4 times 15, that's 25. Now right here, this is going to be really big. Let me grab my calculator. 16 times 15. And so that's minus 240. So obviously you don't need to get exactly the number here. You can just tell it's going to be a really big negative. Since this is a negative discriminant, we have no real roots. We have imaginary roots because square root of a negative equals I. Over here we've got 4 squared. 4 times negative 1. Lots of negatives here, be careful. So we have 16. So this is going to be negative times negative is positive. Positive times negative is negative. 16 minus 16, we've got a 0 discriminant. That means we have 1 real root. And finally, we have negative 2 squared minus 4 times invisible 1 times negative 7. Oops. This is going to turn into negative 4 times negative 7 is positive 28. 4 plus 28 is 32. Since I got a positive discriminant, this means 2 real roots. Okay, now what would these look like if we sketched them? A no real roots graph means it's hovering somewhere above the x-axis. A 1 real root graph means it's touching 1 time. And a 2 real roots graph means it has 2 roots touching right there. Okay, how'd you do?